Are we on?
Just started. Okay, yeah, all
Oh,
good.
okay. Okay. So hello everyone. We're going to spend next 45 minutes to 1 hour discussing on a very high level what Kafka Streams is and what all can we do with it. And at some levels, we are also going to discuss the architecture, a high level view of how the architecture and what goes on under the hood. Okay. So, so what is Kafka Streams? Kafka Stream is an event streaming framework, which is native to Kafka ecosystem, which means that on the source of a streaming application, we are only going to have a Kafka topic. On the other side of the Kafka Stream application, it can only be a Kafka topic, meaning that you can't have a Kafka Stream application read from a file and write to a database, for instance. You can only read from a Kafka topic and you can only write to a Kafka topic. Um, Typical features of Kafka Streams application are very similar to any other streaming framework. It supports real time or near real time transformations. You can do joins, you can do stateful operations with Kafka Stream applications, and that's something that we're going to have a look at in the demo. So I'll jump right away into a demo, and the demo is a very simple one. What we are going to do is we are going to ingest a string, simple string, a text-based data into a topic. And what this data is, it basically is um, this data is about a game, and the points that the user are making on that game. So what the data that we have is the user ID and which game did that user ID play, and how many points did he or she make, and the time at which these points were logged in that stream. So here user ID is going to be the key to the Kafka message, and the value of the Kafka message, the message body itself, is going to have the game ID, points, and time, as you can see here. And in that Kafka Streams application, what you see in black forms the topology of the Kafka Streams application. What we're going to do is we're going to filter out bad records. What are bad records? Bad records are the ones where there is no game ID. That's my definition of bad records. So these records will go away, and we are only going to be left with just this much, right? And then we are going to try. Now if you see the game ID, some of these have got underscore, some of these have got a hyphen. We are going to use a flat map processor in this topology, which was going to you know transform these game IDs into a consistent format by removing all the hyphens and underscore and changing it to uppercase. And that's what get produced to the Kafka topic. So let's have a look at how this application is working. Then we'll go through a quick walkthrough of the code, and then we'll jump into the architecture. So okay. So I have created the topics already, user points and user points clean. So user points is basically the input topic, and the user points clean is basically the output that I showed you. So I'm going to, okay, I need, all right, I'll just fire up Kafka. Hmm. Okay, so I have the console producer here. Where this is where I'm going to put in my data, and on the right side, I'm going to start up consumer, which is where we'll see the transformed output. All right, so I have the input topic here and the output topic here. So as I push the data here, we should see the output here. And before we move forward, let me just fire up the um, application. Rebalancing to running. So my application is running, and let's produce some data. Let's see. So I'm going to put the data in here, and let's see what do we get. We get G1 here. Okay, so there were some messages unread by this application. So this is the output that you see. But let's put some more messages in there, like this. So as you can see, what's happening is the this G hyphen one hyphen was removed, and it gets converted to uppercase, and I was removing all the hyphens from this value, so hyphens are removed also from everywhere, if you see, right? So this is a simple application which in real time can transform a streaming data. And now let's have a look at the code, what we are doing in there. And after this, we'll go into the architecture. So this is going to be just a functional walkthrough of what a Kafka application looks like. Now here, the very first thing that we're doing is we are getting the configurations from a file. Let me show you what the configuration looks like. So these are the configurations. So you have to supply application ID, and I've given it the name demo1, and what is the bootstrap server, and the auto offset reset policy for the Kafka applications. Now, the very first thing that we have to do is we have to create a stream of the data out of a topic. So stream K stream is the abstraction on Kafka topic or a streaming data. And what I'm doing is I'm using a streams builder to get a stream of this topic, which is user hyphen points. And here I'm saying what is the type of the key and the value. So I'm saying that I want to my type for key is string, and the type for value is also a string, and that's how I'm consuming it. And after the user point stream, I'm applying a filter, which is what we saw in the diagram. And this filter takes a predicate. The predicate is it's a lambda, but rather than showing you as a lambda first, let me just quickly show you. So this is basically the filter which implements a predicate interface, and we this is the method that we have to override, which is where the logic for filtration is. So any value which does not have at least three fields, or exactly three fields, and if the first field in the in the value is empty, then it is going to be filtered out. It won't be allowed to pass to the next processor. But I've written this as a lambda expression here. There are two ways in which you can do it. Either you can create a class the way I did earlier, and then you can create a object of that class. That's what you can pass, or you can take a lambda expression approach, which is what I've done here. Then once you have the filtered stream, we have to then transform that value by removing the hyphen and the underscores, and converting from lowercase to uppercase. So what I'm doing here is I'm using a map values method, which is available from in this framework, and I'm using this particular class which implements a value mapper. And the method that we are overriding here is called apply method, and basically what I'm doing is simply replacing hyphens and underscores, and converting it to uppercase. A very, very simple operation, nothing very major here. And once I have that particular stream, I am writing it to a Kafka topic called user points clean, right? And here again, I have to tell how am I, what is the type of the data that I'm producing. I'm saying my key is string and my value is also a string. Rest of the code is boilerplate, so let's not worry about that. But this is basically the Kafka Streams application that we just saw. Now, under the hood, let's have a look what's happening, or let's try to understand what the Kafka Streams architecture looks like first. Now, when we are so what we saw in the code basically was defining a topology, right? Topology is this yellow box that you see here. It's basically a logical representation. The topology would exist in this form: state store. Maybe if there is a state store, for example, in the example that we saw, that there was no state store, there were just 2 or 3 processors, and that would be the logical representation of what the actual application would look like. Now, once the application is instantiated, um, when we start the application, what happens is the Kafka Streams framework creates tasks, and the number of tasks is that it creates is exactly equal to the number of partitions of the topic that you're consuming from. So, for example, if I'm consuming from a topic A, which has got 4 partitions, the total number of tasks that the Kafka streaming framework is going to create is 4. Now, if I run the application only one instance with only one thread, that application is going to all the 4 tasks are going to be submitted to the same thread. Now, the moment I create another instance of that application, there would be a rebalancing that will kick in, and the tasks are going to be moved out of that particular instance to another instance. Okay. Now, about the Kafka, the app, this gray box that you see is basically a running or the physical view of how the application, the Kafka stream application, looks when it is actually running, and there are 3 parts to it. One is the consumer part, the producer part, and this is the same as the Kafka consumer and producers that we know. And what gets added onto it is the topology, the tasks, basically. When the topology is realized, when the application is started, that's what the task is. Now, then, as I said, the number of tasks is exactly going to be equal to the number of partitions that are there, and it is going to be evenly distributed across various threads that are there. So this is how the Kafka running Kafka application looks like. Now, what is happening under the hood? Let's try to understand. So this is the topology, and this is basically what I define in my code. Then this I have created this. Just a second. I've created this topology, and I've defined this topology to start reading from a topic called A, which has got 3 partitions, and I've color coded these partitions. Each partition has got its own has its own color. Now, when I submit this application, what happens is the Kafka streaming framework is going to create 3 tasks. So what you see here is basically the task. Why 3 tasks? Because there are 3 partitions to the topic. Let's say if there was one more topic which has got 4 partitions, and my Kafka streaming application, this topology was to consume from both the topics, then the number of tasks that is going to be created is going to be equal to the maximum, basically a function of max of the higher number of partitions that are there. So if there are 2 topics A and B, one has 3 partitions and one has 4 partitions, the number of tasks that are going to be created is going to be 4 and not 3, always the higher one. Now, then I start the application, only one instance with one thread only, right? This is one instance and one thread only. What is going to happen is that all these tasks are going to be scheduled on the same thread. Okay. If I were to start the same instance with 2 threads, what would happen is then it would look like this. I mean, this is not to suggest that I can create another thread but the application is running. I started one application with 2 threads. So this is how the allocation of the task would be. Now, let's say this is the running state, and all of a sudden the volume increases too much and I'm processing a lot of data, and I'm maxing out on this particular instance. So I can have one more application instance where and with only one thread. So in that case, what happens is the Kafka stream framework will automatically move one of the tasks out of this into this particular thread. And if I start, let's say, another instance with just one thread, we can very well imagine that there are only 3 partitions. So the maximum number of active instances or the maximum number of active tasks that we can have is only 3. So this application instance is going to remain idle. Of course, if any one of these application instances goes down or crashes, then the tasks are going to be moved out of that particular application instances into this instance. Now, so there are a few things that I want to talk about here. Fault tolerance specifically. Let now assume that there is a this topology is using state store as we have discussed. Now, if let's say this particular application instance crashes, application instance 2 crashes, so of course the Kafka streaming platform is going to move the task out of this particular instance into this instance, because this is an idle instance and it'll be moved here. So the state store is basically maintaining the state of the instance of the partition that this particular task is dealing with. Now the color coding, I forgot to mention, the color coding is of a lot of importance here. Each task is tied to a particular partition only, and that never changes. So if this particular yellow color, so yellow task is for P1 and this is dark yellow for P3 and orange is for P2. So if this particular instance goes down, then the same task, when it is brought up on application instance 3, it is always going to be consumed from P2 only. Now when that happens, the state that was maintained for all the data that is processed out of this particular partition also has to be built all over again, so that when the application starts resuming, it is exactly in the same state as this particular instance was before crashing. Now, if let's say there's a very heavy application that we are processing, the heavy data that we're processing using this application instance, you can very well imagine that it may take a very long time for the state store to build up, and eventually the amount of time that the application instance 3 takes to bring up the task will be very long. Now, how does Kafka handle that? First of all, the state store state is maintained at a partition level, so which means that it's not like the whole state of the topic is going to be maintained in the state store. It is only for that particular partition that the state is maintained here. Then every time there is an update to the state store, there is a corresponding change log topic. Now, what is change log topic? So let's say in my application, I'm maintaining a state where I'm storing the latest points of each of the users, for example, and in this particular instance, what happens is, if this particular application so the change log, sorry, the change log topic, every time there is a change to this particular state, let's say for my ID, the score changes from 10 to 20, for example. So that particular data is going to be put into a Kafka topic also, the change log topic also, and that change log topic is co-partitioned with the topic from where we are reading, right? So that change log topic is also going to have P1, P2, P3, 3 partitions, and the corresponding state is going to maintain in the corresponding change log partition. So the change log topic will have partition 2, which is going to have the state store change log for partition number 2, the partition that it is processing, and that change log can be replayed when we have to instantiate this particular task on another instance, on application instance. That entire change log is replayed to build the state store. Now, if it has been a very long running application which has been running, let's say for last 2 or 3 months, you can very well imagine there might be a lot of data in that topic. So in order to deal with a very large topic, what happens is, these state is obviously by a key, right? So the Kafka messages are keyed in the sense that there's going to be a key against which there's going to be a message. So what happens is, this change log topic is a compacted topic, which is to say that that whole topic is going to have value against one key only. So you cannot have, let's say, if the key is Akash, so there cannot be 2 records in that particular topic where the key is going to be Akash. So if Akash's score right now is 10, and if it updates to 20, there's going to be a message going. The message is going to be produced to that change log topic with the key as Akash and the value as 20. and there is a process running in the background which basically checks for duplicate keys, and it deletes the duplicate key. So the so 10 Akash colon 10 is going to be deleted, and the only thing that you're going to be left with that in the topic is going to be Akash and 20, which is the latest record for that key. So a log compacted topic is a topic where the only the latest record for each key is maintained. So there is never a duplicate record. There is never a duplicate key in this topic. So that way, the changelog topic is a very small topic because the duplicate keys have been removed, and that compacted topic is replayed to recreate the state store. That is how the fault tolerance is achieved. Okay. And now, what all can you do with the Kafka stream? You can have typical ETL use cases here, where for extraction, Kafka has another utility called Kafka Connect, where you can source data from any of the source systems, such as any database or a file or whatever, and then you can transform and load it into another system also. Then there are real-time transformation use cases. You can perform stateful operations such as join, aggregation. You can do windowing, a lot of things. You can have Kafka Streams application also come with the capability of an API, REST API layer. So you can actually query these state stores can actually be queried using a REST interface. So if you want to know the current state of, let's say, what is the latest score for a particular user ID, you can actually query the REST interface, and the result is going to be given right from that particular state store. Okay, so what makes Kafka Streams so popular? Kafka Streams is native to Kafka, which means quite a lot of parallelization features. The fault tolerance features is exactly the same as what Kafka has to offer you on that front. So which means with replication, it provides fault tolerance. The unit of parallelization is achieved by having many partitions, and so on and so forth. So a lot of the things that you get with Kafka Streams it comes from a Kafka world, and hence you feel right at home. The Streams DSL is very easy to use, and quite a lot of it's very comprehensive, Streams DSL itself. But there might be a situation where you may hit the wall, and you want to implement some use cases which the Stream DSL does not offer out of the box. Then you have processor API, which is basically defining your own logic and your own things that you can't do with a typical Streams DSL API. So it is extremely extensible also, which is what makes it powerful also. And this being very simple is another add-on to what Kafka Streams API has to offer. Okay, now we have looked at demo 1. We are going to move to demo 2, but before that, if we have any questions, we can discuss.
Maybe I'll start first, Akash.
Yeah.
So at any time there'll be two copies of the state. One in the local state store, and the other one is in the state logs. Is it the change logs?
The change log, yes.
Okay, so there'll be two copies.
There will be two copies, yes. The state store is it can be in memory or it can be a persistent store. Typically, RocksDB is what powers these state store. So the change log is just as a fault tolerance to provide for fault tolerance.
Okay, but how does the exactly once semantics come into play? For example, if there is a downstream processor which is also receiving, and then the upstream processor goes down. So is it something like it will wait until the state is built and then it will start to stream from where it left? Is that how it works?
No. So the topology. So this processor, this is atomic unit. So if the data is read here, then the whole topology, the whole task is going to be executed. And if, let's say, the state, because the state store, it's not immediately written to the state store. It is written in the cache first, and that it is flushed to the state store. And if, let's say, this is a single unit, it's a monolithic piece. all these processors are a single task. So if there's a failure, it's a whole failure. There's never a case where one processor fails and the other is still working. So it'll fail as a whole.
No, the scenario is top source 1, and there is a set of processors writing to source 2, and then from source 2 onwards there is another set of processor as a processor
Another is
taking
application itself.
Yeah, it's the next stage, let's say. So from yeah.
Okay, so so this is one application. Okay, so this is one application. What we are saying is that this one application, streams application, is producing to a Kafka topic, and after which there is another streams application. Let's say this application, which is consuming from here and writing here. Is that the scenario? Okay, so these are two independent applications, right? So what gets this will have its own. It will only commit to the messages that it has consumed and it has processed.
Okay, so application 1, when it comes back, it will make sure that it will not
reproduce the messages
which is already pushed. Okay,
which is already pushed. Yes.
Okay.
Yeah.
So can I have a view of application 1 and 2 in a single unit, or it's always application 1, application 2, and from a deployment perspective, we'll have to manage these as two independent units, not as one single unit, is it?
Two independent units. Yes, this will be. This is one streams application. This is another.
So we have to submit application 1 and then submit application 2, and then monitor both. Okay.
Yeah. There will be, and each running it in its own JVM. Two applications.
Okay, thank you. That's all for me.
Yeah. Okay. If you don't have any other question, then we'll move on to the second demo, which is an extension of demo 1. Here, what I'm going to demonstrate is the joining capability. Now, what I want to show here is that in the previous example, we had arrived at this stage where we were able to filter and transform the data. Very simple transformation. Now, here, what we are going to do is we have a user profile topic here. That this user profile topic has got the profile information of each of the user IDs. Like for example, user ID 101 is Akash. He lives in India. He's a male and he's so and so age, whatever, right? So those kind of data is there in this topic, and we have a requirement where we want to enrich this particular user points stream with the information of so I don't want 101 has scored 10 points and he played game 1 and so time. What I want is user ID 101 played G1 and 101 is Akash and he lives in he's a resident of India. He's a male, and other profile information. So basically what I want is enriched stream of the points, right? Now let's have a look at the code first, and then we'll look at the demo. Now the code is here. So up until this point, it's the same. It's just that if you compare it with the previous application, I have chained the method calls. So I had a user point stream, and then up on top of user point stream, I had a filtered, and then from filtered, I had a transformed user point stream. Here, what I'm doing is instead of having these as individual k-stream objects, I'm simply chaining it, right? So I'm streaming it, then I'm applying a filter, then I'm applying a map values to change from lowercase to uppercase and removing hyphen and underscore. The second step is where we are trying to join the data. two tables, two topics basically. Now, what I want to talk about here is the notion of k table in Kafka stream. Now, k table, as we just discussed, the compacted log topic, compacted topics, is what comes into play when we are talking about a k table. Now, what is a compacted topic? We just discussed, right? So the Kafka messages, each message has a body, it has a value, it has a key. A log compacted topic will not have duplicate keys, which means if I put a message now with key as 101, for example, okay, wait a minute, I'll in fact demonstrate this. Okay, so what I've done is I've created a user profile topic already, and I've configured this topic to be a log compacted topic. Okay, and I am going to produce, let's produce some data to it. Okay, in fact, I've already produced this data to this topic, and if you can see, 106 Akash India mail and 106 Akash Dubai mail. So the key is 106 106, but I'm producing it twice. So what the expectation is that whenever that background process which cleans up the Kafka topic runs, it will remove this particular entry because it is the older entry for 106 key. So what it does is it checks whether the key is already there in the topic or not. If the key is already found, then it checks which one is the older message and it removes the older message like this. So this is the only thing that should be there in the topic. So let's produce one data. Let's call it 107 and John, he's in Australia and he's a male, for example. If I produce this data, user file, let's say okay, so if you see there is 107 John. Okay, now when I change it again, okay, when I change this data again, and if the log processing, and let's say he's moved to New Zealand. Okay, but the log, it won't kick in. Okay, wait. Okay, I'll demonstrate it in a bit when we are running this application. Excuse me for that. So the point I was trying to make regarding the k table was that it's a log compacted topic where there is no duplicate key that is allowed in a given topic. And if you do produce a duplicate key, the older entry from the topic is going to be removed by a process. And we're going to have a look at that demo just now. Now, what happens is we use the streams builder to get a global table. And this basically is the abstraction of a log compacted topic. The k table is an abstraction of a log compacted Kafka topic. And we have a user profile topic from where we are getting this abstraction for global k table. And I'm saying again that it's a string key and a string value. Now, once I've done that, I've got a user profile table here and I've got a user point stream here. And all I have to do here is that in order to join them as user point stream dot join, and I have to supply what is the table that I'm joining it with, and what is the logic to join. And first of all, what is the key selector? So I want to join on the key of the message, and this is what I'm saying, that I want to join on the key, because both these topics, the user profile topic has a key as user ID, and this k stream user point stream also has got the key as a user ID itself. So which is why I'm selecting user ID as the key. Then in this particular, and then the third argument is the logic to join itself. And my logic to join is very simple. I simply concatenate the user point record with the corresponding user profile record that I find for that particular user ID, and I using a comma, right? And then once, so this will give me a join record, but I want to apply another map function to it to transform, because I also want to see in the value, the Kafka value, the user ID also. So this map function will take the key as the user ID, and then the enriched record from the join previous operation. And this enrich, what I'm going to do here is that I am producing the user ID and the enriched. I'm adding user ID itself to the record, the enriched record, and then I'm producing it a user points enriched topic. Now let me start the consumer. Okay. What we're going to do is, let me push the same data again, and okay, now we have to start the application. Okay, so we just pushed this data, if you remember, 101 and 103. So what is happening here is that we are getting the enriched data, and what we are getting here is that 101, it is transformed up until this point. And if you notice, we have got the profile information of the user ID 101. Similarly, we pushed 103, which happens to be Jaideep in our case, and Jaideep lives in Japan and is a male, so it is joined. Now, about the log compaction, right? About the K table, let me demonstrate the feature now. Let us say Raja has decided to move from Russia to US. So if that were to happen, and we'll see if we get the results. So in the profile topic, earlier the user 101, the record was Raja, and he's in Russia and he's in male. Now I'm going to change that to Russia and US and male, right? So I'm producing this data again. So what has happened is, now there is a new entry in that topic, which has the same key, and it's a key which is already there in that topic. So now the ideally what should happen is that I should, if I push another user point record here with 101, I should be getting Raja US male instead of Raja Russia male, right? So let's try and push one record. He played game 2. He made 25 points, for example, on 2020 0109, and some time, let's say it's 13 30 and 20 seconds, for example. Now when I do that, if you see, what I'm getting now is Raja US male. Now why is this happening is because the process which cleans up the topic behind, in the background, has removed the previous entry for this particular key, and it has kept the latest entry, which is Raja US male. And hence, when I'm trying to join it now, you can see that the value, the user profile data for the user 101 is now updated with US. Right? So that's basically how the join would work. Now, the Kafka, the K table. So now let's try to think of a situation where, let's say, the just a second. So this is my Kafka topic, and it's basically a stream, user point stream, let's say. Right, and I have another, and I have a user profile, which is configured as a log compacted topic. Profile topic, which is log compacted. Now, I want to ask, we saw that there is each application instance or a task is only consuming from its own corresponding partition. Uh, let's say there are 4 tasks and each is consuming from P1, the second is consuming from P2, and so on and so forth. When we try to join, how many partitions should this particular topic where I have the user profile have? Can it have like 3 partitions? Can it have, or should it be having the same number of partitions as the stream topic that I'm joining it with, or can it be some other number? Any guesses?
It can be anything, I suppose.
Yes, so it can be. So there are two. So there are answers. There are 2 answers to it. It can be anything, and it should only be. It should be co-partitioned. Now, and there are pros and cons, which is what I want to talk about. Now, let's assume the case where where it has to be the same. Now, if it is the same, then my streaming application only needs to maintain. So it's a stateful operation, as we can imagine. The join is a stateful operation, which means when I'm trying to join, it is going to maintain a cache. So the approach that I can take is, in my stream application, I can maintain a copy of the log compacted topic in my streams application. So either I maintain the whole topic in my application so that when the incoming data for my partition comes in, let's say 101, I can look it up in my state and I can find out. And because I have the entire topic, that means I can, any data that comes to me, I will definitely be able to find that out if at all it exists in the user profile, right? And the other approach is I only maintain the data in my cache only for the partition, the corresponding partition of the user stream. So if I'm maintaining it for the whole topic, then I need not have the same number of partition. I can only have 3 partitions, or maybe 10 partitions, whatever it is, because I'm maintaining the whole topic in my cache. But if I choose to not maintain the whole topic in my cache and only maintain the corresponding partition, the requirement then becomes that it should be co-partition. When I say co-partition, the number of partitions should be the same, and plus the key on which the partitioning is happening also should be the same. So that for a given user ID 101 in the stream and 101 in profile topic always lands in the same partition. Only then will I be able to look up. Otherwise, the lookup will fail. Now, what are the pros and cons? If I have a existing topic where the number of partitions are not the same as the one that are there in the stream, then it makes sense to have everything in the same topic. But then the downside of it is that you're using quite a lot of memory because you're having to cache everything. Compare that to a situation where you're only having to maintain or cache a corresponding partition. So that would be, so now the abstraction, there are 2 abstractions provided here as such. Global K table basically will have everything, the whole topic is going to be maintained inside your streams application instance. So if I'm running 3 instances, then each of the 3 instances will have the entire topic cached into it. The other abstraction which is provided is a K table, which is, you can guess, it is only going to keep the corresponding partition. So if this application instance is assigned to read from partition number 1 of the stream, then it will only get the data for K table from the user profile topic partition 1 only. Okay, so that is another thing that I wanted to talk about.
Akash, just a doubt here.
Yeah.
Sorry.
Yeah.
When you say that there can be a same number of partitions, it actually depends on how this global table is being used, right? Because that profile table could have been used by multiple streams, different
Yes.
tasks, basically.
Yes.
So that way we may not have an opportunity to have same number of partitions everywhere.
Exactly, which is where you will have to use a global K table.
Yeah.
Yes.
Got it.
But if
Yeah.
you do have that opportunity of defining how many partitions to choose from, and the way you're producing message to both the topics, user streams, and because even if you have the same number of partition, let's say if there's a different a key using which the message is produced to user profile topic or streams topic, even then making using a global K table would make more sense, because then you can define your own key on which you're wanting to join. And doesn't it is not requiring you to have the same partition key also, because you have the same number of partitions, but then the data may not land in the same partition really, because you're using a different partitioning strategy.
Yeah, exactly. And in that case, when the partitions are varying and if we have multiple streams available, that means we may have to cache the user profile data into multiple, the whole topic into multiple streams. Isn't that correct? If say the user profile table had millions of records, that means we have to cache that a number of times, right? In different.
Yes, it will be duplicated in across all the number of streaming applications. So you're running 5 instances of your application, then all those 5 instances will have the whole topic cached.
Is caching only the solution here, or is there any quick lookup kind of a thing in the global table?
Yeah, so the state is maintained. The state is powered by a persistent state store.
Okay.
Yeah.
Which means it's not for the developer to manage it. If I just use the global table interface, this framework takes care of it. Yeah.
Yeah, the framework will take care of it.
And all I have to do is to allocate enough memory, enough RAM, and if it spills out of the RAM, it should be managed in the disk. It's all should be taken care of. Yeah.
It should be taken care of. Yeah. Now, I'll just quickly have a look. Kafka streams demo. So see, we were running a demo 2 application where we did a join, right? This TMP Kafka streams is where this is partitions. Okay, can you? No. So it is the global state store. Can you see? It has created a global state store. If you look at and it's a RocksDB instance. This path is configurable, so don't go by this. But what I'm trying to show here is that the user profile state store is maintained here. So what happens is the join happens on top of this particular RocksDB instance. So when I'm joining, actually the query is happening against this RocksDB, and the background, the topic is also being cleaned. So can you see it's like the global store is maintained here?
Yeah.
Yeah, Akash, I have one question. We were saying that in K tables, when there are multiple records with the same key getting inserted, after some time, whenever the process run on the background, it cleans up or it kind of suppresses the older one, and you can see the new one as whenever you query to that K tables, right?
Yeah.
But is there at a frequency at which it runs the cleanup
Yes.
process, or is there a trigger which is
Yes.
making it clean the table?
There is, yes, there is. So this particular thread, which is responsible for cleaning up these Kafka logs, you can set how frequently should that thread run. It's available in the broker configuration itself. I don't remember exactly what that configuration is, but yes, to answer your question, there is.
If it is at a frequency, then there can be a time at which when I query, there can be two rows belonging to that key, right? So what will happen in that case? Will it run two rows, or how? I just wanted to understand.
The latest record is going to be retained. Now, how does it decide latest? So there is a notion of time with each. So each Kafka message has got 3 components. One is the header, one is the key header message, and there is a timestamp component also. Now the timestamp, either the producer can define what the timestamp for each message is, or if the producer is not defining, then by default the log write timestamp is what is assumed to be the time of the Kafka message. And if let's say there are 2 messages in a Kafka topic which has got the same key, then the time the message with the latest timestamp is going to be retained, and the message with the older timestamp is going to be removed.
So that means that the API which is serving the data, that will always return the latest. It's only about the persistence of that data which will get cleaned after that process runs, right? But the API is always returning the latest one. So for an application which is querying, it doesn't have to worry about if it is going to
yes,
give
because it is not happening. I mean, if you look at the code, really, you get a feeling that the join is happening directly on top of a topic, but really what's happening underneath is it's creating a rocksdb instance, and the rocksdb instance is basically it's like a state of that particular log compacted topic, user profile topic, and the join happens on top of that rocksdb instance. So hence the rocksdb instance always maintains the latest copy, and hence it is able to return the latest copy. Even though if I were to replay this topic, this particular user profile topic, you will see that for Raja there will still be 2 entries, because Raja Russia and Raja US, because the thread which is supposed to clean this up has not run yet, because I had shut down my Docker, and I have not really changed how frequently this should run.
Actually, it shouldn't matter, right? I mean, this thread frequency is only to reduce the size of the topic, but in terms of data integrity, it has no impact.
It has no impact.
That is what I wanted to confirm, because according to me, if it is running momentarily, there can be duplicate records available, but the API is not handling all that. So for me,
the mental model is when the so in that global streams, in that topic we are publishing duplicate records, but then downstream in the user points stream in this example, when you join, you are actually reading from that topic, right? From that global table topic. So when the newly published duplicate record comes into this, but the framework is actually trying to update the key value store within that, right? So as you update, you are already overwriting the old one with the new one, which means at the time of joining in the downstream, in where Akash is pointing, you only have 1 copy. Although the upstream topic has 2, you read the new one and you have only updated your internal state. You will only have 1.
The
so
state has
absolutely no issue.
1 copy,
no issue with data integrity. But the cleaning up of in the upstream global table is basically to reduce the size of that topic, because you don't have to keep the duplicates there anymore. So that can be a periodic process.
I think it's kind of compaction which happens in Couchbase behind the scene.
Yes, and if you come to think of it, I mean, yes, completely. Sorry, if you come to think of it, there is no impact so far as the application is concerned itself. If this application, however, were to go down, this particular instance, and it were to come up somewhere else, the problem, if the log has been compacted already, then replaying that particular change log is going to be much faster versus a situation where the log has not been compacted yet, because the frequency is too less. That's the only implication of how frequently the logs should be compacted, the Kafka topic should be compacted. But functionally, there is no implication. Recovery would be faster if the frequency is higher, but then it has got other implications, right?
Yeah.
Okay. Now I have another demo, and this is an interesting one. This is I've given it a name called stateful filtering, where what's happening is I'm getting some data. I'm getting a customer ID along with the time and his or her location information, and I'm supposed to process this data. It's a lot of data that is flowing in, and I'm only interested in, let's say my use case is such that I'm only interested when the customer changes location. So I know the customer is location A. If the customer remains to be at location A and I keep getting the same information over and over and over again, it doesn't make any sense for me to process it. Only when the customer changes from A to B, I'm interested. And that's really what I want to pass on to the downstream application, let's say. So if a customer is changing the location, only then we will forward this to the downstream application over a Kafka topic, else we will suppress it. This is basically demo number 3, and this this demo actually requires us to instantiate a state store ourselves and query that state store also. So I'm going to run that demo very quickly, and then we can wind up. So this particular code. Now here, a very simple use case that okay. So here what's happening is I have a stream builder, and with that, and I also have got a store builder. This store builder is basically within the Kafka streams framework. If we have to get a store builder, this is what I use. And what kind of store you want. You can either have a persistent key value store, or you can have an in-memory key value store. It supports both. I chose persistent key value store, and I'm giving it a name. And I'm saying what is going to be the key, what is going to be the value, and there is a time, system time that I'm giving. This is basically the time of instantiating this particular state store. Right now, I add that state store to my stream builder, and in the stream builder, what I'm doing is I'm getting a stream of stream out of a topic called signaling. This signaling topic is going to get all the data that we just discussed, where it has a user ID and the location information along with the time. And I'm saying that my input data, the key is a string and the value is also a string type. And I'm using a transform method. Now, transform within the Kafka streams application or the API, transform is a stateful processor. When I say stateful processor, that means you can use this particular processor to update or read the state. And what I'm doing is I'm supplying a signaling filter supply, which is basically a transform supplier. I'll show this code to you just now. And I'm passing in the name of the state store, which will be used if at all it is required in this particular transform processor. Now, if we go to this particular method, it takes a transformer, and it is supposed to basically, it overrides a get method, which is supposed to return a transformer. And this transformer, so what I've done is, it can be a bit difficult to read. I'm returning a new transformer, which again is an interface, and I'm implementing the interface right here. As you can see, I'm initializing this in this particular key value store. I've taken a private variable key value store. I'm initializing it, and all I have to pass is the name of the state store as I declared it here. And this particular state store, here in the key, the transform method, which is basically what gets called every time there is a key. So the key of the message is a string, and actually in functional terms it is imz. The key is imz, and the value itself is the signaling record. And this is basically the signaling record, how it looks. Sorry, imz, and it is going to be like this: time, lag, cell, and IMEI. And the state store contains the key as imz, and the value is going to be time, lag, and cell. This is what I'm going to store in my state store. So every time there is a signaling record that comes in, I'm going to go to my state store and see whether this imz is there or not. If it is not there, then this is for the first time I'm seeing this particular user. I'll just simply forward it. But if it is there, then I will compare the lag and cell. By comparing lag and cell, I can find out whether the location is changing or not. If it is exactly the same, then I'm going to suppress it. But if it has changed, I'm going to forward it, right? So that's what I'm doing, and the logic is here. If the last known time and location equals to null, which means we have not seen that particular imz before, I'm going to update my state store, and in my state store I'm putting the imz, and along with imz I'm putting the this particular thing, time, lag, and cell. That's what I'm putting in the state store. And if I have seen it, then obviously I'm going to compare whether the last known location is equals to the current known location. And if it is not the same, which means it has changed, then I'm going to forward it to the next particular record. Otherwise, I'll suppress it. Key value store. Okay. Okay, let's have a quick demo of this one as well. Okay, signaling. So I'll just prepare some records here. MZ is one, some timestamp. LAC 1, sorry, cell 1, and some IMEI I1. Let me start this application also. Okay, so it has started, is in fact process some data also. Anyway, okay, so I'm putting a data with 999. This has never been seen, I know that. So if you see, no last known location, last known time and location found for MZ 999. Wait a minute. So it has recognized that there is no last known location for 999, and if I put this again, the same record, if I put again, maybe a time would be, let's change the time a little, 4000, but it's the same location, same IMEI, same cell and LAC. So so current time is this, last known location is L1C1, and again L1C1. So it has found out that it has not changed. And if I change it now, I'm not producing it to any topic, so I won't be able to show you the output to a topic though. So let's say the location LAC ID changes to L2, and this remains the same C1 and I1. And location is a function of both LAC and cell. So even if one changes, the location changes. That's how it is going to be interpreted, right? So if I do that now, what this says is that the location has changed, or it has been more than 10 minutes. So I have two things: either the location changes, or it has been more than 10 minutes since the MZ was last seen. So in either of the cases, it is going to be it is going to be considered for forwarding to the downstream system. Now, one more thing that I'm going to do is I'm going to keep the location same this time, but I'm going to increase the time quite considerably to make it more than 10 minutes. And I'll keep the location same, C1, I1. If I do this, hopefully this is more than 10 minutes. Yeah, so again, if you see, the location has changed, or it has been more than 10 minutes. So again, it has recognized that it was seen more than 10 minutes ago. So it will forward regardless, because it is important. So the way this application logic was written is either the location should change, or it should be the last known location should be more than 10 minutes old. As simple as that. So this is what I wanted to demonstrate. And let's again have a look at what we have in the TMP. Temp Kafka streams. Now, can you see there is a signaling app? Now, why signaling app? Because that's what we had named our application. Can you see? I'm naming it signaling app. So it creates a RocksDB instance there, and it only has got one topic and one partition, and it has created its rocksdb instance here. And signaling store is the name that I had given, if you remember. Here, signaling store is the name that I've given. So, and this is where all the data is maintained, and this is binary. So, right, so it has created its rocksdb instance where it is maintaining the state, and it is able to query that state, update it also, and so yeah. So here, if you see the last known location in the previous instance, this is the current time from the stream, and it updated the the state store. And the next time when we push the data, which was for more than 10 minutes, if you see here, it has updated to the last seen time was updated here like this. So this is
quickly jumping into some broader questions, Akash. So does it work with the cluster managers like Eon and Mesos or anything, or do we have to manage it ourselves?
It has to be managed by ourselves.
Okay, so which means the number of instances of applications that I'm spawning, everything is managed by us only.
Yes.
Okay, that's a little strange. Okay.
I'll just conclude this very quickly, and we'll open up some questions. So for further reading, we've got these things that we can go through. Table streams duality. It's a very important concept so far as Kafka streams is concerned. Join. There's something called as windowing, which is to say, let's say for example, there is a stream of user points flowing in, and you want to if you want to ask questions such as, in last 5 minutes, how many points did Akash earn, for example. This is where you would use something like a windowing. So it's like a slice of windows over which you do aggregations or mathematical operations or whatever. You basically have these windows within which you perform all the it's like a micro batching thing. So you batch over, let's say, a 5-minute window or a 30-second window, and you perform whatever your operation you have to perform on that batch of data. And that you can group that by key and do a lot of other stuff. Interactive queries is another features which basically is a REST API which is exposed on top of a Kafka Streams application. So you can use these REST endpoints to query the state of particular whatever data that your application is dealing with. Then there is something called as KSQL, which is a very powerful abstraction on top of Kafka Streams. You can use SQL-like syntax to spawn these streams applications, and you can perform all sorts of things such as joins, windows, aggregations that we just discussed, transformations that we discussed, and it is even extensible. You can define your own user-defined functions, which you can invoke in your SQL statements. So you can have your own functions, and you can use them in the SQL statements to. So that makes it even more powerful, because that makes it extremely extensible. And then one thing which is gaining quite a lot of traction is you can build Kafka streams using a Quarkus. Using Quarkus, which is basically a framework for creating native version of your applications, which is known to have lesser footprint and on both on the CPU and the RAM. The boot times are faster. So this is again something which is gaining quite a lot of traction. These are the things which we can go and read further. Now this is something. So thank you. This is where we've.
This is where my question again comes in. In the interactive queries, if they are actually querying on that state store, if there is no notion of there is a cluster, no notion of cluster, no notion of how many instances of applications are running, how would the interactive queries work? Now I had that question, but then I am thinking now because of the Zookeeper, because every time I spawn a new instance of an application, I'm sure my consumer gets registered in Zookeeper. So probably this writes on that to understand and then to parallelize my queries. Yeah. That would be a way. I'm just guessing.
Yes, that would be a way. So let's say if I query a data and I've got 5 instances running of my application. There are 10 partitions to the topic on top of which the streaming application is running. and there are 5 instances. So 5 application instances. So there are 10 state stores maintained for each of the tasks, each of the 10 tasks that is going to be spawned running in 5 application instances. If I query the first, it's not like I'm going to go and query. I as a consumer of that API need not know where my data resides, which application instance hosts the data that I'm wanting to query. So what happens is this logic of redirecting the request to the correct application instance has to be written when we are exposing this particular API. So when I'm exposing such APIs from my Streams application, I have to ensure that if a request arrives for a key which this particular instance doesn't host, that application instance should then forward the query to the right instance using the metadata request to the Kafka brokers, and find out which application instance is hosting it, and then get the data from there and then respond back to the consumer of the API.
Yeah. Any other questions before we stop the recording? Okay, all seems good. I'm going to stop the recording. Thank you, Akash.
Thank you.
Thank you, Akash.